All right, let's go through a few conceptual questions. Go ahead and read through this. What do you think the answer is? Okay, correct answer is B. Some of you may very well use wrenches a lot, and you have your extension rod. I believe they call it a cheater bar sometimes. So to turn and tighten this nut, we're applying a force at some distance, r, from the rotation axis. Oops, sorry, that can help. The rotation axis in this case is the nut. And that's true in any case. The second situation is most effective because R is bigger. Since torque depends upon how long that lever arm is, how far away from the rotation axis we're applying the force, and then the component of the force that is perpendicular to that. In case B, the torque would just be this total distance R, so the length of the wrench handle plus the length of that additional rod. That biggest R applied with this force gives the biggest torque. The force and R, the angle between them is 90 degrees. Sine of 90 is 1, so I'm not going to write the sine of, or just the sine of 90, though we can. Option A is R times F as well, but R is smaller. The angle between these is 90 as well, which is what we want. Option D, that angle's 90, that's what we want. But having the bar in that orientation is not helpful because that doesn't extend the distance from the rotation axis. I mean, technically we can say this distance is bigger, going straight from the nut to the end of the rod, but the length of the rod is parallel to the force. So it does not contribute to the torque in that case. In option C, similarly, all we would care about is this Y distance, because that's what's perpendicular to the force. So C would give us the smallest torque. It still would give us a torque, just not much of one. A and D are tied. And then option B would give us the largest torque. Let's look at another question. What do you think in this case? Okay. The correct answer in this case is A. Now, it is important to know where the rotation axis is. So rotation axis is in its center. That is explained by the rod pivots on an axis through its center. That's what leads us to know that. So force C is a large force, but it's at such a close distance. So when we talk about R and the perpendicular component of force, R in this case is simply L over 4. The force is 2F. So the torque here is 1/2 LF. This, just for practice, this force C would make the rod rotate counterclockwise. This problem isn't asking for a direction, but I want to practice that while we're at it. If you put your fingers in the direction of R, So lever arm always starts at the rotation axis and points out to where the force is applied. Put your fingers in the direction of R and bend them towards C, the force. This comes from the cross product. Put your fingers of your right hand in the direction of R, so your fingers would be pointing to the right. Bend your fingers this way. So in the direction of the force. I'm having some serious lag time here. Your thumb is the direction of the torque. But the direction your fingers are bending excuse me, represents the counterclockwise. Okay, side note done. Sorry about that. So for force B, we would draw the lever arm starting at the rotation axis out to where that force is applied. The torque, R times F perpendicular, R is L over 2. The force is simply F. So we get 1/2 LF again. And by the way, this one would also be counterclockwise. R, put my fingers to the left in the direction of R, bend them towards B. Pretend your fingertips are arrow tips. You would see your fingers going counterclockwise. Finally, for the force A, I would draw my lever arm starting at the rotation axis, go all the way out to where that force is applied. So that total distance L, but this force has X and Y components. I only care about the Y component of the force because that's the one that's perpendicular to R. Well, the Y component of the force will be F sine 45. Sine of 45, square root of 2 over 2. It's bigger than 1/2, so this one is biggest. It is also counterclockwise. Excuse me. So A is correct. Even though it's not completely perpendicular, that larger lever arm makes it bigger. Let's look at another example, or another question, I should say. What do you think about this one? Okay, the correct answer is B. So rotation axis is right here in the center. We have to know that to talk about torque. So again, torque, RF perpendicular, or F, R perpendicular to F, either way. At this exact moment in time, we would draw R exactly to the left. We always draw R starting at the rotation axis and draw it pointing over towards where the force is applied. The force is the force of gravity of this hanging mass. So the torque right now is half the length of that rod or bar times mg. And it's causing counterclockwise rotation. Just side note. As the bar rotates, though, the bar will rotate, so there will be a moment in time where the bar is at some sort of angle from the horizontal. So I drew in the rotation axis again so that I can draw R. R starts at the rotation axis and goes out to where the force is applied, the force is still mg straight downwards. Now up here, the angle was 90. They were perpendicular to each other, but now this angle is greater than 90. Meaning we either need to break the force into components along the rod and perpendicular to the rod, or we could break R into components that are horizontal and vertical. If we do that, the torque now is just X. That's the distance that's perpendicular to mg. X is smaller than R. So this torque is now smaller than it was when the rod was horizontal. And it will continue getting smaller until the rod is vertical. When the rod is vertical, R, the lever arm, it still always points along the rod. It starts from the middle where the rotation axis is and points out to where this force is applied. But now these are parallel. That's not how you spell parallel. Meaning there is no torque at this moment. So we're going from a maximum value of torque when the force and the lever arm are perpendicular. We're getting smaller and smaller as the rod rotates. We're at zero torque when it's exactly, the rod itself is exactly vertical. Now the rod would probably rotate a little ways to the other side and then come back to an equilibrium, but it would take some time. But ultimately, the torque is going to decrease because the angle between R and F is changing. It's getting bigger. Now, one other side note. As I mentioned, we can, in this case, break mg down into components, one that's perpendicular and one that's parallel. We would want this side, this mg. In this case, we're defining that as phi. So mg sine phi there. But again, the component of the force that's perpendicular to the rod is smaller, so the torque is smaller. When we go to calculate torque, either way is fine. It doesn't matter if we break R into x and y components or force into x and y components, essentially. We just have to find the component of the force that is perpendicular to the lever arm, or the component of the lever arm perpendicular to the force. Let's look at one more concept question. What do you think about this? Correct answer is C. So there's a pin over here holding this left end of the rod in place. We can consider this the rotation axis. We know the scale is pushing upwards. The reading on the scale is how hard it has to push upwards. Excuse me. We know this mass down here, 1,000 newtons, is pulling downwards. If somehow the scale could magically disappear, the mass at the end would cause the rod to rotate clockwise. The scale is not allowing that to happen. The scale is causing a counterclockwise torque while the mass is creating a clockwise torque. Since this rod isn't going anywhere, then the torques have to be the same. Meaning, R times F for the scale has to equal R times F for this hanging mass. So if R is half for the scale than it was for the hanging mass, then the force has to be double what the hanging mass is. That's not how you spell double. That's where we get the 2,000. Double the force because we are at half the distance. The torque is always dependent upon R, lever arm, and force. A smaller lever arm requires a larger force in order to have the same amount of torque. This particular problem is an example of what we call equilibrium. Specifically, static equilibrium. The rod is staying stationary. We're going to be looking at some equilibrium problems. Earlier in this semester, the only requirement we talked about was the net force being 0. And that's because we were pretending everything was a point mass, essentially, and not needing to account for where the mass was or how it was distributed. It turns out the full definition of equilibrium is that there is not any type of acceleration in terms of tangential or angular. So there's no speeding up or slowing down. Specifically, static equilibrium is an object staying at rest. Dynamic equilibrium is an object rotating or moving with a constant velocity and or constant angular velocity. So we'll be looking at equilibrium here in a video or two.